So this is the last session for these 3 days of summer school. Remember that tomorrow we have a workshop. And it's a great pleasure to have Professor Neil Lawrence here. So Neil was my PhD supervisor 15 years ago, perhaps.
Goodness, yeah.
in this very building.
Yeah.
And we just thought that for this last slot, we were going to be doing something different. So rather than having a lecture, we're going to have more like a conversation. So I'm going to start asking some questions and comments, and then if people in the audience want, to ask their own questions, they're just feel free to do it. Okay?
Sounds good?
Sounds good? Great. So, so you started GPSS, I think it's, what was it, 10 years ago perhaps? But before you had the round table, with Carl Rasmussen, Chris Williams.
Yeah.
They were involved in that. What were you thinking when you started GPSS?
So I think, well, the whole tradition of these meetings goes back to a really weird time when the community was maybe like 600 people in total, like at Neurix, of whom maybe 20 were Gaussian process people. And so you could get them all in the same room. And at the time, the methods that were dominating were kernel methods. And there wasn't any understanding in the kernel community. I mean, it's odd now because we're the same community as them now, really, aren't we? But within that kernel community then, there wasn't really any understanding of all the capabilities of a Gaussian process. And I was confused by this. But I noticed I'm very friendly, I always have been with Bernard Shulkov, and one of the things he was really, really good at was community building and doing these edited volumes. And you can go all the way back to the early days of kernel methods. They had this workshop at Neurix, and I sort of felt, oh, maybe we weren't doing that as well in the Gaussian process community. So we started having small meetings where we got people together in Sheffield, I think in about 2005, where we started sort of hammering out what we thought the key questions were. And those are just great meetings with really nice people. And I think when you look at the questions, the papers that we were discussing, many of the key questions that we were asking then are still key questions today. And one of the things that sticks with me, and the reason why you're being inflicted with a conversation today, instead of like a talk, is because one of the processes of those meetings is we would call in like the old Gaussian process experts, including like Tony O'Hagan, who we had in Sheffield. And I remember asking Tony, and I can't remember which meeting it was. I was like, it might not even be my meeting, it might be someone else's. And I was saying to him, oh, they're really keen to get you along to go and speak at that meeting. And Tony said, oh, I'm not sure if I've got anything new to say. And I was like, but what? But you don't say anything new. You've got all this experience, all these things that people are really curious about. And I remember being really surprised that Tony was saying that. And I think, when I think back, I think Tony was a little bit older than I am now, but not a lot older than I am now. And I'm just starting to feel the same. Partially because, as Tony felt at the time, as he saw Gaussian processes moving from statistics to machine learning, so it's at a different scale now, but we were working on these things much more rapidly than the statistics community was. And I think he felt he was losing a bit of touch with what people cared about. And the interesting thing, two things happen. That happens, but then also sometimes people forget the fundamentals. And you're kind of not sure what the fundamentals that they've started to miss. So we would all sit there and listen to Tony, sort of like going, oh, he's got such insight and whatever else. But he had no idea. He just constantly felt, I guess, that we were going beyond him. And I started thinking, oh my God, that's how I feel now a little bit about this. We're working on all these really cool and interesting things, some of which I'm aware are possible, and some of which I'm not aware that you're doing them or that they were possible or what the directions are anymore. So it feels a little bit odd if you stand up. Having said that, I am giving a one-way talk at the moment. Giving a one-way talk about your perception of the way things are when you don't feel quite in touch with it anymore. Yeah. So I think that for me, academia and machine learning has always been about community and about conversation between people. And I think you just get to that point in your career sometimes where you feel you're trying to do other things to support that community in other ways, and you feel a little bit detached from that community and that conversation. But the reason for creating those meetings and for running GPSS, I mean, we got to some point where we did the meetings, we'd established the questions, but then the next thing happened. And there was the book. The book was the Rasmussen and Williams. And Carl and Chris finished the book in Sheffield at one of those first meetings. They actually, I put them in a hotel together, and they used a room in Sheffield to put the finishing touches on the book. And so that was like 2006, and that was a really amazing moment, because all of a sudden all of these things that we knew as a community were out there, and other people knew them, and then they were using Gaussian processes with these knowledge. But by the time it got to like 2013, that wasn't true anymore. And then you had this sort of slight problem that I was finding, that every new student who came into the group, you were having to tell them the same set of things every time. Right? One-to-one. Oh, no, it's not quite like that. Yeah, I know that's not in the book, but what we realized is this, you know, blah, 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 blah. And that's how GPSS started, because I think the first one, I just emailed, you know, basically the gang that had been, I mean, it's not quite the gang, because it's some different people who come in, but some of those, the people and their students and their collaborators and other people we'd come across and said, hey, why don't we just get together, and instead of having to talk about all this material another time, let's get together in Sheffield and share it with the group. And I think in that sense, I don't know, is it saying too much? And you would know more than me, that I feel that in that way, GPSS has been like a living book that has shared that knowledge and that understanding across the years.
And it's quite interesting because you have students that then become the lecturers, and that's happening since many years ago.
Yeah, and I find that process, I find it actually a little bit, I get a little bit emotional about it, because I think that you're seeing the next generation coming in and learning and taking these things forward. And for me, that's like the heart of community building. So, and I love that community building process. And we've done it, I mean, the GPSS model, 3 days summer school and a day workshop, was also then later so I guess first GPSS is like 2013 or something.
Yeah.
And then 2015, we take the model to Africa, with Data Science Africa, with an extended workshop thing. And the first one's actually GPSS, but it's like the 0 version. And after that, it became data science. And now you see the same thing happening. What you're doing here, people do it in Africa for the whole of data science. And it's just this extraordinary community. And it started out with us coming in and teaching, and now it's all taught by local people. I mean, I give a lecture, some silly thing like this, you know. But that community building is just so critical, I think, to everything that we're trying to do.
Yeah, and besides GPSS, during those years, we were also like traveling all over the globe, doing these GP road shows.
Yeah.
Remember, you came to Colombia. I think you also went to South Africa. You went to Italy.
Australia, Italy. Yeah.
And obviously, like, you know, you have young audiences, lots of people eager to learn about GPs. Do you see differences between those audiences? I guess each contest has its own challenges.
Well, Colombia was the best, obviously. Yeah, it was. I mean, I think, I'm sure it was the first one. You said 2014. You sure it wasn't 2013?
No, it was 14. Yeah, 14. I remember that was the year of my wedding, so.
Obviously, the GPSS took priority. Well, the first thing you learn is that when you go to the equator, they don't actually have a summer. So the notion of a summer school doesn't make any sense.
Exactly, yeah.
You have to have a wet season school, or a dry season school, or this sort of thing. And that was like, so the first couple then were, so actually the, I can't remember the ordering of these things, but the Columbia one was what I used, and I was sort of teaching it. By the way, when you learn to teach, like, the efficient way of teaching is prepare for each lecture. But if you're teaching a whole summer school in a week, and then you're preparing lectures, you're delivering them, you're staying up, or you're getting up early in the morning to do that. And that's what I sort of did, we were talking about that earlier, in Columbia, to prepare material, which in some sense, so the Columbia Roadshow, as we used to call it, was like it's the most complete version of here's everything Neil thinks about Gaussian processes. Because I sort of did everything, right? Yeah, after that, we always had other people. It was long, and we always had other people doing things. So in some sense, that was the thing that was long enough to mean that I had the confidence to launch GPSS. Okay, what are the differences between the audiences? Yeah, absolutely. And I think one of the things that, so when we did Uganda, Kampala, I mean, that's what sort of really opened my eyes and my interest in let's think and talk about real-world data science problems. Because there, you know, the students were very keen, but what John Quinn, who was there at the time, used the school for is he sort of advertised it and allowed it to bring in various people like the Ugandan Virus Research Institute, etc. So there were more diverse interests, and there was a lot more interest in problem solving. And you see, I think that GPSS is kind of quite problem solving focused, but Data Science Africa is completely problem solving focused. And I find that actually, I think particularly like in the mess of machine learning at the moment, I find that really grounding to like be focusing on problems and to be doing things that, and I think it is hard as well. I think it's, you know, the sort of standard Europe thing we're doing, like let's invent a new challenge and solve it, it's fun, but it's actually relatively easy to do versus here's an actual genuine problem people care about and we're going to address it. And it flips everything around because, of course, if you're in GPSS, you're sort of leading with the model, you know. Whatever your problem is, we're going to fix it with a Gaussian process. Whereas if you're in Data Science Africa, it's the other way around. You've got a problem and you're going to search around for the best solution. Yeah. And it turns out to be a Gaussian.
Yeah. So I think one of the things that I really like about GPSS is how we combine theory with practice. So we have these lab sessions in the afternoons, and people come and play with notebooks. And I remember when I joined the group, you were like a big advocate of good software practices and you know open source software, and you see that when you run the notebooks, there is like a shadow of those principles and practices there. What is your reflection these days about that? I mean, because there's been an explosion of frameworks and things that you can do with GPs and frameworks like with automatic differentiation.
Yeah, I think it's the thing I'm sad about in some sense, is when we started out, one of the problems I felt we had is that it was a funny time, right, because actually we were pretty quick on Python. It was MATLAB, right, when we started. And one of the thoughts was that we needed to move. If you were in a computer science department, like when we were here, and you were trying to get master students to switch to MATLAB for their project or whatever, it just felt very awkward all around. And so it's actually when we were here, wasn't it? You were working in MATLAB still, and part of the group, like Nicolo, started working in Python.
I remember you giving one of the seminars in the ML group. You just presented Python as, guys, Python.
Yeah.
And this is how you do things in Python compared to MATLAB.
And no one believed it. And I think that one of the things was that scikit-learn didn't exist, right? So this was a big problem. So I actually started trying to rewrite some software, basic machine learning software. I mean, but, you know, I didn't have enough time or whatever. And I remember Gavin being really skeptical in that seminar. And we were sort of pushing for that for a while. So actually, by the time we got to Sheffield, I think we had a group where pretty much everyone was convinced, apart from Andreas, who was working on deep Gaussian processes. And the reason he was still using MATLAB was because the code he needed to do deep Gaussian processes was so much more involved than everyone else, right? We couldn't just pick up. I mean, we eventually did it in Python. But everyone else was on Python. And it just felt like this really interesting opportunity to build an open source using the MATLAB code. Everything was based on the MATLAB. We'd done all our object structures in MATLAB. We knew like what made it flexible. redo that in Python. And that's what GPy was. And then the thing about it was going to be that, let's make this open, let's invite everyone to contribute, and then we'll just have this place where we'll have like the ultimate Gaussian process stuff. And I think the thing that I didn't quite foresee is, everyone else is like, we never published GPy. We never published GPy. There is no paper on GPy. And that was purposeful, because we never wanted it to be, look at us, we've created this thing. And this came to me because we had in Sheffield, Fabian Pedregosa visit. Do you remember that?
Yeah.
And he was one of the scikit-learn people, and we talked about it, and he said, well, I said, well, what's your, we asked him loads of stuff about how you build an open source software community and all this stuff, and he shared loads of learnings with us. And one of the things that stuck with me is that he sort of said he felt very guilty about the fact that like scikit-learn is always Pedregosa et al. And he's getting thousands of citations for it. And although he triggered it, he wasn't, I don't think he's actively involved anymore. And this really struck with me, and it struck with me in a couple of ways, that something goes wrong with that in journal papers as well, that like, you know, a lot of people contribute various things, and then whoever's written this journal paper, they're getting all the credit. And so I got very interested in, we should be making journal papers more like software, not software more like journal papers. So we didn't publish GPy, and that was kind of with the intention that it could become a community effort, and we could build a community thing behind that. And that really didn't happen, because I think what happened after that is everyone else saw it as an opportunity to publish their own frameworks. So instead of saying, let's contribute, when it came to automatic differentiation, when it came to all these additional things that we would love GPy to have, and maybe it was too hard for them to contribute, maybe we didn't get the community right, but then you just get the proliferation of effing frameworks again, which is probably natural. I mean, it's so interesting. And that I think that's put us in a difficult position relative to what we were trying to achieve, which was to be in a position where it was, and maybe this is harder with Gaussian processes with neural networks, where we could make progress by having a shared set of software. And maybe we just don't understand enough about what the algorithms are. Maybe we still don't, right, in order to do that. But in some sense, that still held us back. So that vision was there. Yeah, I guess it's not really being realized. Whereas the community thing, so those two came together, like GPy and GPSS were always there together, right? But the community's there, right? You know, it's just somehow it doesn't feed back into the software.
Remember that you have questions, you can ask them. Henry.
Should we start working on large language models?
Yeah, I don't know. It's interesting, isn't it? I mean, if you do, you're going to be there with everyone else, right? So it's my interest has always been in the community differentiating. Like, how do you? Because I can't move as fast. I once wrote a blog post that talked about soccer. It said that like you've got, when you're doing research, like the most exciting bit is like those games of soccer that you have on children's playgrounds, where there's like just a mass of people trying to kick at the ball, moving around, chasing after where the ball is, right? And I was never very good at that version of soccer. There were some kids that work, that like would emerge, yes, I've scored, yeah, me, you know, and then you don't know how they're doing it. But the version of research I like is the one that's more like the way, and by the way, proto-football was like that. So it's interesting, like rugby, American football, soccer, all have the same origins. They all started from a bunch of people running around after a ball. The shape of the ball varied, right? So the one was easier to pick up, the other one rolled along the ground. So one was dominated by kicking, the other one was dominated by holding. And then you get Aussie rules, you get all these different forms of Gaelic football, everything, right? So it's sort of but there was the proto version is let's just chase this thing. Now for me, I don't like that version of the game because I think I'm much better spent having time to reflect on stuff. And so the problem with large language models is it is in that position, right? And even if you want to be in the game, you know, and I'm lucky because I know so many people who are in it at the cutting edge of it and they'll say all these different things. you seems like you have to have quiet access to compute and everything else. Now, it doesn't mean you can't, I don't know. I mean, and I think this is, the weird thing about it is like, it's odd to think that across my career, things have changed so much since the early days of machine learning to where they are now. And the thing that I feel is that these new capabilities, you know, it's an order of magnitude more change on very widely across society, because people you can talk to a bloody computer now in a way that is unimaginable for us. And many of the ways that we think about, so much of what GPSS is about getting you to think in a way where uncertainty is being quantified in such a way that you could work with an engineer or a scientist to help them understand the nature of uncertainty. And we know how difficult that is to educate, like all these paradoxes around uncertainty and probability. So the chances are that that's going to be the mechanism of of communication for regular people to interact with computers is minimal. And it's kind of mind-blowing that you can even think about the idea that you may be able to deal with the uncertainty by talking to a machine. I mean, we're definitely not there with the models at the moment, but you can, it's something conceivable, right? That you could sort of, instead of saying, here's the error bars, here's the process, that you could talk to the thing about the patient, and it would somehow, by having a good model of you, it would know what to say to encourage the right level of uncertainty in your head directly without showing you an error bar, right? That's now achievable, it feels to me, in a way that, and I kind of find that concept mind-blowing. So I don't know whether it's, I don't know what anyone should do. I don't really know what I should do. But I find that interface, I find two interfaces very interesting. When I think about large language models, I've started to call them hands. And what do I mean by hands? I think what you've got is people, why is there panic and confusion? There's panic and confusion because people in the wider world are used to digital computers which can't make mistakes. And they can't make mistakes because they're based on logic and they're programmed. And so they've been told that AI is going to happen, and that whole premise of AI was initially based on we'll build knowledge from the ground up using logic, right? And no one's ever told people that, yeah, the thing you're getting is not that. It's utterly different. What we're doing is now we're reading every human text that's ever been written. And then we're using that to distill human reasoning into a machine. So what that means is that, and why do I say ham? I think of it as a human analog machine. So a machine that is analogous to humans, right? So if you go back to the days of analog computers, what an analog computer is my favorite example is something called the Moniac that's in the Science Museum, which was built in the 1940s, and it's a bunch of pipes where the water flow through the pipes represents movement of money in the British economy. And you change valves, and that's changing interest rates. And then you look at the balance of payments, and different tanks fill up. So this is analogous to the economy because water and money both flow. And in that way, what we're building with these large language models is an entity that is analogous to a human approach because it's building, in inverted commas, feature spaces that are related to the feature spaces we use. But the way it's doing that is it's being told, please compress all the text that's ever been written. And the way people are tuning how that's doing that is by presenting more code to make it more logical, or more polite stuff to make it more polite, and then refining with reinforcement learning, right? So that is an utterly different entity from this vision that the classical AI people, and it's such a horrific term, AI. I mean, I'm getting more and more annoyed by the fact that machine learning has become AI, because that is AI. They were going to drive everything from first principles, and it was all going to be correct. And the mission failed, and machine learning succeeded. But machine learning is distinct, because AI, if you look at the philosophical tradition, it's a rationalist philosophical tradition, like going back to Wittgenstein. Whereas machine learning is an empirical philosophical tradition. And the vision you're getting with this hallucination is the conflation of the two. Because people are thinking, oh, this thing talks like a human, therefore, and it's going to be superhuman, therefore, superintelligence, we're all going to die. I mean, it's just absurd. As soon as you realize, oh no, that's something different. That is like a reconstruction of the human analog machine. The sort of things that we care about, and I think a lot of us might be interested in for UQ, that we can do with the computer, which is simulation, where we're building a digital simulation, which is, where maths is in effect the analog to the real world, right? That is allowing us to talk about weather or climate or something like that. And of course that's an abstraction, right? So that's an abstraction. If it weren't an abstraction, we could never compute it. But we're making those decisions about that. Now what's interesting is those models are getting bigger and bigger, and we saw this in the pandemic, where those models are getting so big that the people who build the models don't understand their own models. Same with climate models. So we're getting a really interesting possibility here. So you've got very complex digital computer style model simulation. One of the things that we've been very interested in is how do we use Gaussian processes to help interpret that and distill that and teach scientists about that. But there's a possibility that then you now have the hand, the human analog machine, and then you have the human. So instead of, we're using surrogate modeling to sort of communicate with human experts about what's going on, but you can imagine a world where you have effectively that simulation is digital computer. Then you have the human analog machine, the ham, and then you have the human. And so you've got two new interfaces you're working on, right? One is the interface between your digital system and the human analog machine that is transferring the understanding of what you're seeing in that into the human analog machine. And the other one is a human talking to that thing saying, oh, so will the temperature in Cairo be over 50 degrees or whatever else, in a way that they can understand, right? And I think that that's a really interesting way that things could pan out. Something like that has to happen. The sort of image we're getting of there's going to be one big LLM to rule them all. I don't think that can work. I mean, maybe it can. I mean, I was asked this at the House of Lords committee meeting yesterday, could we bridge between the hallucinations and the correctness? I don't know exactly what everyone's up to in that space, but my favourite way of trying to deal with that is separate these components out. Separate the logical model that you're interested in that is representing your best understanding of the physics of the system from the communication component, which can now look at this very vast system and give you answers that were very difficult for an individual to look at, and then the human themselves. Sorry. Yes, so work on that.
Are there any other questions?
There must be more. Could be about anything. Who's watched me lecture? I mean, because one thing, you may have watched me lecture on YouTube anyway. One person, two, there we go, 2, 3, 4. So yeah, questions from those things I said in the past. Do I believe them anymore? Or do I think it's, yeah, go ahead.
What's the difference between kernel methods and Gaussian processes?
I think it's like a lot of things in science. It's a philosophical difference, isn't it? One of the things I think about a lot in this case, and it's caused a lot of confusion in the past and will continue to cause confusion, is that there's this sort of world of things we want to do, and then there's the world of things that we can mathematically represent. Which, to a first order approximation, is like linear algebra or something like that. So when you're trying to traverse these worlds to answer questions, it's like you're traversing a sort of, I always love being in Sheffield and the countryside and the paths. So it's like you're traversing that countryside. You're following the paths through the countryside. You could be off the path. You could be in the heather or in the bracken or in the brambles. But you rarely are, most of the time, and you don't make very good progress. So what happens is you're journeying along these areas and you're meeting other people. And they're using the same maths, but they're using it for a different purpose. So philosophically, the different purpose was, historically, but I think people have got a really good understanding that the way the worlds were slightly different is one group of us were interested in this as a way of sustaining a distribution of functions. Another group of us were interested in this as a way of building classifiers where they could give some performance guarantees under empirical risk extensions, right? So what this leads to is you're doing a lot of related stuff. You can learn an enormous amount from each other, but sometimes you get in these really crazy arguments that occur because no one ever asked where the other person was going. So you're sort of like with this person that's working on the same bit of maths, You're working along together, and it comes to a fork in the road where you could make two different choices about which maths you do next, and you have this enormous argument about which the right fork is to take. Because no one ever asks, well, were you going to St. Ives or were you going to Huntingdon? Right? And the truth is that this comes up all the time between statistics and machine learning, and the traditions in machine learning, the traditions in statistics. And as a result, you get these sort of fractures between these communities and people pointing at each other and calling each other idiots. And this actually comes back to something that is also fascinating about people, is that you sort of think, you might think that people who live in the same area would get along well. I mean, and they kind of sometimes do. But the people they hate most are also the people who live in the same area. So Manchester United fans hate Manchester City fans. And everyone in Manchester hates everyone in Liverpool. And everyone in Sheffield hates everyone in Leeds. I mean, they don't, but in general. And it's kind of partially because if someone's totally different from you, you can just shrug and go, oh, they're totally different. But if they're superficially mostly similar, but different in one way, people seem to get really annoyed about that. So a lot of these barriers in the community are really down to that sort of weird cultural thing, and about ideas about, okay, the big one between machine learning and statistics is about the difference between why you're doing it. And machine learning people have always been trying to get a better prediction. So they didn't care about explanation. Whereas statistics people have always cared about getting a better explanation and caring less about prediction. And again, that's a different fork in the road. So, interestingly, in statistics, I'm not sure, well, Grace Barber did a lot of stuff, and I would say she's more of a statistician with splines, so sort of regression methods. But you don't tend to find people using kernel methods in statistics. You tend to find them using, you tend to find people using Gaussian processes in statistics. But one of the things you have to be careful of is very, very often in geostatistics, it's a noise model. It's not the function itself. What they're trying to build is a linear model, but it's a spatial linear model, so they have a covariance function to handle the noise. And that's hell of a confusing thing if you're used to using the covariance function to model a function. Because you make so many different choices, right? If you're trying to use the covariance function to model the spatial residual, one would say, right? Because you're actually caring about your linear model because you want a model for explanation, right? That's what a statistician will do. Whereas a machine learner would say, why would I even have this linear component? I can make a prediction with this complex covariance function and just drop the linear component. And you see that coming up all the time. And one of the things I've said in some of my lectures is, so the nice way to deal with that is if you are building models and you care about your parameters, use beta like the statisticians, because then it's clear what you're doing. And if you don't care about parameters, it's just for prediction, use W like the machine learners do. Because these are different things that if you work in data science, you want to do those different things at different times. And I think that is the modern world, that we need to be better at moving across these fields. Because the reason in the old days they had to stay within their fields and care about this is because they didn't have computers. So they couldn't try any of this in practice. So they had to sit there for ages working out the maths before they decided what method to use. That required a lot of intellectual effort and communities that were doing that together because the computation was the expensive part and the intellectual effort was cheap. Nowadays the computation is cheap and intellectual effort is therefore relatively expensive. So you tend to see people moving across these fields a lot more.
Going across those lines of the kernel methods, I've heard of deep kernel processes, they switch on processes, they're really good.
To each other.
Yeah, GPs, I mean these GPs.
So deep, I don't know what people are writing in the latest thing on these things, but so deep kernels go all the way back to a paper by Lawrence Saul where he was composing kernel methods together. It's a very, very interesting paper. And I guess at that time, I can't remember if he was trying to really push it for fitting. I think then there's a new wave of deep kernels that emerge when deep learning's emerged, and I've never understood if it's useful or what the point is in it. Maybe there is a point, but I kind of feel it was just riding the hype wave. The reason being, because the deep kernel method, if it just, so you can compose kernels together, right? Why can you compose a kernel together? Because you can kernelize a kernel. Because kernel methods are like, oh, I've got an inner product, I'm going to replace the inner product with a kernel. And like, whenever you think about kernel methods, the kernels you mostly use have inner product inside the nonlinearity. So you can build another kernel by putting another kernelizing that inner product. And that to me is like the deep kernel trick. It's kind of obvious that you can do it. The follow-up question is, why am I doing it? The answer, to get a neurospace. But not anymore, but when they did it, right? But I think the interesting problem with that is that, like, it's still, from a Gaussian process point of view, it's still a Gaussian process, obviously, because it's a kernel. And the whole point, for me, in a deep Gaussian process, is it's not a Gaussian process, right? So you go to the deep Gaussian process because you look at the world, and you've worked on Gaussian processes for a long time, and when you first saw them, you just thought, this is the most remarkable, amazing thing. And you could even see the weaknesses in the framework, because you were like, I can have priors over distributions of functions that look like that, how cool. But then later you find out, well, yes, because the derivatives of Gaussian are Gaussian, of the Gaussian process are Gaussian, that means that the derivatives of your process must be Gaussian, which means that you can't have jumps in the process, right? Because if you have a process with a Markov jump process, Maurizio worked on this stuff, we tried to do this stuff way back, didn't we? We got sort of really interested in how can you integrate, what were those called, those processes?
Ullstein OU process?
Not the OU ones, no, what's the stuff with the CAD lag and everything else? What's the name? What are they called, Rich? The ones that you can't write down that cover all the Levy processes.
Levy processes?
Levy processes, which are a class of processes that include Gaussian processes, but they include Markov jump processes. And there's this really nice, there was that Matthias Winkel talk we went to back in like 2006, wasn't there, where you can decompose these things in terms of their characteristic function. And the characteristic function makes it easy to add processes together, right? So with a Gaussian process, you can add two Gaussian processes together because Gaussians add to Gaussians, and that's fine. But with most processes, if you add a Poisson to a Gaussian, you're moving outside the spectrum of the process, right? But you can do that with the characteristic function. So there's some sort of decomposition of the Levy process into these three component parts, which I'm trying to remember. That one is the characteristic function of a Gaussian process, one is the characteristic function of a Markov jump process, and there's another component as well. Now the problem with those things is you can't write them down. You can't write the likelihood down, right, for anything other than like the Markov jump process, the Gaussian process, and all the processes you will know about, right? So Matthias Winkel did this great talk that's still online from that stochastic processes workshop thing that we were at in Cumberland Lodge, where he sort of went through all these things, and he's a probabilist, and probabilists are like people, they're like the pure mathematician equivalent of a statistician. They don't want to think about how their thing's going to be used in the real world. It's not about the application of it, it's just about the marvelous maths. So he did this great talk, and then he sort of said, and if you want to use these things in practice, here's the examples. And you just get put back to the things that we use. So the point in the deep Gaussian process is it's a way of expanding the range of probabilistic stochastic processes that you can deploy by using stochastic process composition. So by feeding one process into another, you can change the nature of the output functions. The challenge with it is that, of course, you lose the analytic tractability. But because it's based on these components, there are Gaussian processes, and we have this range of approximations for doing that, you can start looking at how you fit those things through approximations. And that's kind of what we've seen. You're not getting that out of the deep kernel method, and I think one of the problems, one of the reasons why a lot of people don't see the difference is because they're not caring about these things from the lens of uncertainty, right? They're caring about these things from the lens of getting a neurospace. No, sorry, from like, I don't know, trying to compose features or something like that. I'm not sure that deep kernel methods really help with that either. I've not really used them. I'm just one of these, I just don't see the point. I mean, like, it's an idea that I thought about and realized, well, that's not going to do it. So you move on to deep Gaussian processes. But there could be a point that it's just that it isn't well covered. But the Wishart things, well, there's always this thing, and also with T processes, that you get, you know, every time you do something with a Gaussian process, someone will come along and say it's a T process or a Wishart process, because that's a sort of extension to make another Murex paper or whatever. I mean, like, you see that trick played again and again, and of course, it's really, really unfortunate that one of the challenges of trying to publish these papers is if you write your paper in that way, so saying, well, basically, yeah, we know you can always extend this in this direction, then your reviewers will reject it. So most papers, unfortunately, will bury, I mean, not even consciously, it's just habitual, it's the process that emerges when reviewers are always criticizing, so they try and bury the connections, I think.
And you know a lot about this because you were program chair for NeurIPS, and then you guys did this NeurIPS experiment.
Yeah, do people know about the NeurIPS experiment? Young people. What we did was, like, when we were program chair, such a terrible job. I can't imagine how people do it now. But I didn't want to change anything because I was like, well, don't make it harder than it already is. But Karina, my co-chair, she said, I don't want to deal with, understand how consistent the process is.
But I think at the time the conference was manageable, no? It was like...
It didn't feel like it, but compared to now, you could say it was. Yeah.
Yeah.
I mean, I think I did AI stats program chair. I want to say there were like, I can't even remember because the numbers don't sound right, like 400 submissions. And maybe we were accepted a quarter, so maybe 100 published papers. It sounds so odd to say that now, right? And then so you got to NeurIPS and it's like 2,000 submissions or something. It's like, whoa.
And now they have 10,000.
I know, it's just like, and at the moment, at that time, we were on this super exponential growth in attendance, but the growth in paper submission was only going up exponentially, not super exponentially. So then what happened was, then somehow the growth in paper submission went up super exponentially after the year I did it. But yeah, so we sort of said, so Karina said, I'd like to explore this. And I think most of because I was the one managing CMT, so I realized how we could do it. And yeah, so we did it. And what we did is we separated the whole program committee into 2 independent parts, and we took, I think, 10% of the papers, and we put them in the system twice. So you've got 2 independent committees. And Claude, this is, okay, one of my most important innovations. How to get CMT to do this. I'm sitting in the bar. I just passed the statue of Archimedes on my walk in. It's looking a bit grotty over there nowadays, but it was a Bath moment. Eureka! I realized, I was like, how do we create 2 independent committees in CMT to do this, right? And then I realized we could do it by creating a dummy author called NIPS 1, NIPS 2, maybe NeurIPS 1, NeurIPS 2 today. And adding, so you distinguish, you duplicate the papers in the submission, and you add this dummy author to each of these papers. It's more detailed than the ones that I know, but... and then you conflict this author. So you conflict, right?
Oh, okay.
So, and then you just write your process as normal. So, and it's like, brilliant. Because it's only all of a sudden you realize you can do everything within the ecosystem of the... Because you don't want to write I mean, I had to write enough code for that anyway. You don't want to rewrite the paper allocation system. So that moment was like, oh, I know how we can do it. And so we did that. Of course, what I didn't realize is that created so many conflicts in the system that when it came to the paper allocation for CMT, the system utterly failed, and I had to rewrite the paper allocation system in Python. So these were unforeseen downstream consequences. And then, of course, the interesting thing was, how consistent are these 2 committees? So, I mean, people who don't know, how consistent would you say that the 2 committees were? And let's say, so the statistic everyone seemed to love, by the way, which wasn't the one we initially published, but you could work out was what percentage of papers would have been accepted in both conferences? People who don't know the answer, what do people think? What percentage of papers are accepted in these two independently run conferences? 5%?
Yeah.
That would be impressive, I think, because at some point that would involve negative information. Because there's some level of accept that is going to occur if you're picking at random. So, and I think that that's going to be, since it's 20 they say 20%, so it's going to be 0.2 minus 0.2. So that would be about about the round. If you did nothing, then you would get. Now, I think you still get more than that because the reject as well. So that would be like you actively managed to do the theses differently. So, because it's equivalent to like 95% consistent if you do the 1 minus. So it's quite a lot higher than 5%. I think, I can't remember what it would be if it was at random, but it was, it's 50%, right? And they repeated the experiment recently, and it's still 50%. And I wrote, I did a whole load of reanalysis on it a few years back, because I kept quite a lot of information about rejected papers. So I actually tracked the rejected papers. And the other thing is sort of, well, two things. We also looked at the paper scores versus their impact, right? So that's for accepted papers, right? So paper scores versus impact. And basically, there was no correlation between the paper score and their eventual impact.
So you measure impact with the citations.
Citations,
Yeah.
so I should say, yeah, so number of citations. So you didn't get any correlation between the paper score and its impact. The fascinating thing was, I looked at a few different scores, and really like with NeurIPS, there's a confidence score. How confident are you in your review? And for that, the confidence score is not supposed to be about the quality of the paper. And that was the most correlated score with impact. It was like 20, 25% correlation. Can't remember, you can see it in the paper. So in other words, people being confident whether they were scoring high or low was indicative of whether a paper is going to be accepted. One of the really sad things about this is my interpretation of that is because papers that are clear are going to be high impactful. But papers that are clear sometimes cause reviewers to sort of go, well, I'm confident and it must be rubbish. Right? So I mean, we made some recommendations in that paper, one of which was to try and extract clarity out and have that as a separate thing, and so that you could do a bit better job, but I don't think any of them have been followed. But yeah, the process of acceptance has a significant component of randomness. Now, one of the things I would say is a lot of people wanted to try and fix that, and they tried to make it more consistent. I think that's an enormous error, because it's very easy to make a process consistent, right? You just accept all papers by everyone's, where the first author surname starts with A. That's a consistent process. It's also a highly biased process. And the challenges in this space is a lot of the actions you take to try and make things more consistent are actually likely to introduce bias. So you know you're going to make errors, and you want to make errors that are not bias errors. You want to make variance errors in the bias variance dynamic type sense. And so in that sense, I think this fear of inconsistency is problematic, because, you know, it's impossible to know what the right level of inconsistency is.
Now they're trying to sort of address those issues with TMLR, trying to accept papers that are just correct technically rather than claiming novelty. Or
Yeah, I haven't tracked it. How's it going?
I think it's good. I'm an action editor, and yeah, you get good papers there.
Do they have a good turnaround? Is it fast turnaround?
They push a lot to make it fast, yeah.
Yeah. But is it fast?
It is. Yeah.
Yeah, it sounds good, yeah.
Yeah.
Was that a question up there, or are you just scratching your chin?
What's the next big thing in Gaussian processes, actually in all of AI? Well,
I don't know, really. I think as you get older, you get less and less certain. The reason was because I used to get asked this question like in the last wave of AI. And like, I was into deep probabilistic models really early on. I sort of left that community because it felt to me that, well, it all became about deep neural networks good, Bayes good, therefore both good, and no one was properly questioning what is this stuff doing and why are we doing it. But I found myself in those early days when I was being asked that question, I would say, well, uncertainty is the important thing, because these models aren't propagating uncertainty, and we know that uncertainty is important. I do think that's true. But then I noticed, as I looked around my wider community, that when anyone was asked that question, the answer they gave was that it was the thing that they were working on before this wave of AI success. So if you were talking to a person who had worked in logic, they would say the next thing is going to be when we introduce logic. And if you were talking about a person who worked on causality, they'd say the next thing is going to be when we introduce causality. And then I sort of thought, okay, so if I'm just saying that the next thing is the thing that I was working on before, and apparently I was wrong in the first place in some sense, I didn't catch the previous way, then I just got really cautious about trying to think that. And so actually, I am, when we went to Amazon, we did quite an amount of fundamental, of practical work, which was driven by the belief that the data inefficiency, and they are highly data inefficient, these neural network models, that the data inefficiency versus, say, humans or even, well, that was the thing. We were like, we could deal with data inefficiency through uncertainty. We knew that was going to help. And so we looked at a number of practical applications where we were going to introduce the Gaussian process at the relevant moment, and we were really hoping to show a big difference in data efficiency. And we weren't able to show that. We were able to show like a percentage improvement, right? We were able to show that, yeah, if you use uncertainty and whatever, you do get a better result. But if you had like, I don't know, some like double the data or 50% more data or something like that, you could get the same result with the neural network. And that's unfortunately not sufficient to justify using the Gaussian process, because the overhead on your compute just people are like, well, let's just collect more data. So unless you're stuck in these regimes, which you often are, and that's where you see a lot of success with Gaussian processes, where data is low, in these regimes where people are doing like image recognition or all these other things, they're just going to collect more data. So it sort of became clear to me that the thing that I had thought the answer was around why, or a significant part of the answer, not all of the answer, why these neural networks were inefficient, wasn't the actual main reason. And I'm much more convinced by arguments coming from causality, and in particular, interaction. And I think one of the things that we're seeing around large language models is kind of interesting in that regard, that people are saying, oh, but they've already seen everything on the internet. Yeah, but now they're seeing things in conversation. And this is kind of a bit of a worry, because that data is being locked away into the large companies that are deploying them. And conversation is an interaction, right? So the field of interacting with someone through conversation may be different from the field of flying a plane through a stick. But most of the things, we evolved with a nervous system for movement, and that movement, like from the earlier stage, has been take an action, sensor response, take an action, sensor response. So the weirdness about most all machine learning algorithms that we've developed is that they sort of developed in the world where the machine doesn't have sensorics that bring it close to the world. So like our nervous system, there's never been a moment when our nervous system wasn't integrated in the world. I mean, something really interesting happened. Like, if you look at, and then the real book to read on this is Breitenberg's Vehicles, which is all about this sort of notion. It's a 1980s book on synthetic psychology. But you go back to the most simple organisms, which are like these sort of jellyfish with nervous systems, and they're just sense and respond, right? And then you start coming up to lizards, and it's broadly sense and respond, because if you look at their neuroscience structure, my understanding, I'm not an expert, most of it is the bits of our neuroscience structure, the cerebellum, the hypothalamus, all the sort of lizard brain, as we sometimes call it, which is all about the motor system, right? They're not sitting there reflecting when they're sunbathing, they're just like waiting to move. And all of that stuff seems really, really difficult. We haven't made any progress on that. And what's fascinating about that is all that came first in human beings, And then this reflective intelligence, all this, even the sophisticated object detection, all the sort of reconstruction of things our visual cortex are doing, the audio cortex, or the prefrontal cortex are doing, is all stuff that came after this interactive world, right? And with our machine learning techniques, what we're doing is this very weird thing that has never happened in the natural world of just having a machine which is consuming enormous quantities of data. There is some interesting interaction going on because the human designer is choosing which pieces of data to put in, and that's shifting how the model goes. But our intelligence and the intelligence of other animals is doing that on an ongoing responsive basis. And the theory behind that is like causality, right? The theory, and I don't mean that there's two flavors of causality, and I think you have to be quite careful because they argue for the same reason we talked about before with statistics and machine learning. And and they don't need to argue because they're trying to do different things. There's the version of causality which is the Pearl school, I would say, where the objective is to try and discover causal truth, whatever that means. Like in statistics, the objective is to discover statistical truth. So you're trying to extend the techniques of statistics to prove things about the world using causality. But then there's the Bernard Shulkop school, which is like causal representation learning, which is just, can I do better learning by introducing notions of causality, which might not be true. There's some sort of potential flaw in them, but they give me representations that extrapolate better in the world. And I'm really interested in that second world as a sort of, it seems to me really, really natural that we're defining our world around us by the way we interact with things, right, at some very fundamental level. And that seems to be utterly the opposite of what's going on with these machines. They're sort of emulating it now. But I wonder if you're going to see a lot of progress in that, because now that you've got machines talking directly to humans, you've kind of got that going on. A question is a provocation of the system, and the answer is the response. And that isn't the data. You get some of that data on the internet under Reddit or whatever. But now those machines are gathering vast quantities of that data.
So I think we're getting to the end of the session. But if you guys want to keep going, we can maybe have 2 more questions.
Should we go there first, because we've had that one, but we'll come back to them.
Just a brief one. Do you think it would be more interaction or synergy between the Gaussian processes and Gaussian data analysis?
Yeah, I mean, this is sort of an ongoing thing, and it's one of the difficulties, because these communities, for the reasons we spoke about earlier, have sort of evolved somewhat in isolation. It then becomes quite hard because the language is just slightly different. Maurizio did an amazing job on this, on the, what's the title of the paper? The
Kernels for vector value functions?
the
Review paper?
The review paper in...
Foundations of Machine Learning.
Yeah, what was it called?
Kernels for vector value functions.
Yeah, kernels for vector value functions, yeah. And Maurizio did an enormous amount of work going through the literature in geostatistics and statistics and machine learning, looking at the terminology and trying to translate it to a consistent terminology, so that when we knew that when we were talking about the intrinsic co-regionalization model, that we were all talking about the same thing. It took a lot of time, didn't it?
Yeah.
And because you're having to... It's like you have to learn... Well, you speak Spanish and English. For me, it's unimaginable. You have to go and read these papers, understand what they're saying, and then translate them. So it takes that... I mean, it's got a lot of citations.
Yeah.
So it is, people do value it when you do it. And I think that's kind of the problem, but I totally agree. The really interesting thing I've noticed is that it always strikes me, and maybe we probably don't have many of them here, but there's a really strong French community in this space that just easily moves over everything. Like if you go to an equivalent French meeting of this, what was it called? Mascot Num? They had this meeting called Mascot Num, and it was some sort of project. And it's funny, the questions, people will shift between the languages of geostatistics and Gaussian processes, as they ask the question, and no one gets freaked out because they're familiar enough with the sort of the semi-variogram and all these things. And I can't do that. I'm not familiar enough with the I have to remember it. I can't speak semi-variogram-ish. But there are people that can. And maybe there are people that can also, maybe they can move into the functional data analysis and understand what was done there and how that relates as well. But yeah, I agree. Is it an area you're in?
Yes, I'm working on it.
And so you're going to write this paper?
The paper is here. Can you check? Can you review it?
At the beginning, you mentioned some key questions in Gaussian processes. Can you, what are now key questions for Gaussian processes?
I was hoping you were all going to,
From a theoretical point of view.
I was hoping you were all going to tell me then. What, I don't know, what are they? What are the big questions?
Well, the only thing that I know was the infinite rank conditioning. Well,
Infinite what condition?
infinite rank conditioning. Like if you have whole information, not if you have whole information, but yeah, you.
Oh, you've got a section of the function.
Yeah, and then condition with that.
Oh, interesting. With what's, actually, I love that because I'll come back to why I love that. But what's the application domain?
I have no idea.
You should submit to Europe. No, you know why I love it? Oh, why was that? Actually, you're making me think of something.
Oh,
Wait, say that again?
Saying that a little bit of that exists in PDEs.
Right, yeah, PDEs. Yeah. Interesting. You know why I kind of think that? One thing I noticed, and this may be known, but I've never seen it used, right, is, you know, like, you've got the sum function, that's sigma, and then you've got integral for the continuous sum, and then you have the pi for product, and then it's like, well, what's the continuous product look like? And, well, it's actually very easy, because you can just map from logs to sums, so you just lose e to the integral of the log, right, and then that's a continuous product. And I've always thought, oh, that should be a sort of long P.
Is that the next thing?
Well, that's the next thing. And then the only thing I thought about is where on earth would one want to use a continuous product? And I said, oh, maybe maximum likelihood in a continuous function. And I don't know if that's how one would do that or if that's how people do it. That's the only thought I've ever had on that space. Because it would then just be a sort of indefinite, a definite integral between the area where you have the function of e to the integral of log of the likelihood. Yeah. Would that make sense? Does that make sense?
I think you also need a measure.
Probably, but I saw, you know, I used to ask Maurizio to go to the maths department.
Go there and ask for measures.
He pure maths, like when he, at some point. Well, he fancied himself.
He got a question about measures theory,
and you should ask it. You go around people like this. If you're not clever like me, but you know clever people, what you do is you should say, so this measure theory, people. How does that work? And they go, oh, you don't need to worry about it. And then I just do. And then what will
I have my friend, who might their friend, who eventually agreed.
I have a really amazing student at the moment who does worry about that and uses it a lot in what they do, Francisco Vargas. And so the only problem is, like, he asks me about that. I said, well, I don't know. I wish the team didn't have to worry about that. So you might well. I mean, these are the fusion processes which you can see for similar reasons. You know, this becomes relevant. And I guess I started thinking about it mostly, well, these type of things because of the Ito calculus and Stratanovich calculus for the work we were doing when you did your PhD. I remember thinking, when we were crossing the road there, I was remembering thinking about that with Carlos all the time.
Yeah.
Oh, well,
Yeah,
are we over time already?
Yeah, I think probably we should just close it there and let's thank Neil again.